When are we going to find out more about TRAPPIST-1? Can any Extremophiles from Earth survive on Mars? And will Artemis make it to the moon, or will there be additional delays? All this and more in this week's question show. It's time for the question show. Your questions, my answers. As always, wherever you are across my channel, if a question pops in your brain, just write it down. I will gather them up and I will answer them here. Now, we do this show live every Monday at 5 p.m. Pacific time. So if you want like the full experience, come and join us for the live show. Get your questions answered. I don't even know what you're going to talk about. That makes it sort of half the fun. And then, of course, we have follow-on questions and a deeper conversation, and we often stretch into overtime, which can go for half an hour longer than the regular show. So if you want more questions, come join us on the live show. All right, let's get into the questions. Stick pictures. I've always loved the idea that the Milky Way is a barred spiral, but isn't that a weird shape for a spinning object in nature? No such thing as a barred whirlpool, right? Do you know what causes galaxies to form in that shape? From the best of what astronomers can figure out, we live in a barred spiral galaxy. And so what this means is that the Milky Way has this central bar that is tens of thousands of light years long. And then you get the start of the spiral arms at the end of the bar. And it's thought that the Milky Way has two spiral arms, although there's still some kind of argument, and it's thought that the Milky Way has a bit of a warp to it. So these are very complicated things to try and figure out, of course, when you're living inside the Milky Way. But astronomers are being able to work it out, thanks to Gaia, of course. And of course, when astronomers look out across the universe, they see lots of other galaxies in various formats. And what appears to be happening is that we see more barred spiral galaxies closer to us, and then we see less of barred spirals, and eventually just spirals without any bars at all farther away from us. And so what that's telling astronomers is that the bar is a more recent formation in galaxy evolution. So early on, you had these small dwarf galaxies that were merging together, and they sort of crashed into, and they added up all of their angular momentum, and you got these spiral galaxies, kind of like a whirlpool. But then over time, what they think is happening is that you get these resonances and interactions between the stars in the galaxy that start to pull these stars away from just this kind of pure spiraling and into a sort of larger structure that starts to form in the middle of the galaxy. And you actually kind of do get that with whirlpools. Like if you mix up some water and you get a whirlpool, you will actually start to see interesting sort of chaotic structures start to form in the whirlpool as it's spinning. And so it appears that it just needs time, that the more time that you've got for the galaxy to evolve, the more you get these interesting structures at the center of the galaxy that form, and they kind of reinforce. So over time, you get more and more of it forming, that it starts to really kind of hold together, and you get this evolution over time of the galaxy. And so this is going to be one of those big questions when you look at some of the big galaxy surveys that are happening with Euclid, Nancy Grace Roman, that you're going to see all of these galaxies right out to the edge of the observable universe, definitely to billions and billions of years ago, and to really get a sense when these bars started to take over and get a way to figure out, like, how old is the galaxy? When do these things typically show up? Why do some of them have them? Some of them don't have them. It's still kind of an evolving question in astronomy. I'm sure you've noticed the Star Trek planet name that appeared over my shoulder. This is a way for you to vote to tell us what you thought was the best question answer this week. And the winner from last week was the question from Tim Ucken about what damage intense solar flares will do to Earth. So thanks, Tim, for asking the question. Thanks to everybody who voted. Now, you're going to see one of these planet names appear beside me for every single one of these questions during the show. We also put a list of them all down in the show notes so you can sort of wait to the end of the episode, figure out what you thought was the best question, and then go ahead and just put that word in the comments down below. That will tell us your vote. We'll count them up, and we will celebrate the winner next week. Jesse Hardy, when are we going to hear more about the TRAPPIST-1 system from JWST? That's really interesting. So I just did an interview today with one of the researchers that worked on the measurements of the TRAPPIST-1b planet in the TRAPPIST system with JWST. So that was the first planet from the star. And this is the one that they were expecting would probably be like some kind of Mercury. It was going to be too close to the star, sun blasted, probably not have an atmosphere, and that was the case. Now, when they looked at the second planet in the TRAPPIST-1 system, TRAPPIST-1c, they were hoping that they would see some kind of exo-Venus, that there'd be some sort of thick carbon dioxide atmosphere, and they didn't see one. And so what I learned in this interview is the techniques that they use to be able to image these worlds. And it's very careful, very meticulous work. So there's two kinds of observations that exoplanet astronomers can do with JWST when they're looking at the TRAPPIST system. One is called the transit, and that's when the planet passes in front of the star. And what you get is you get the addition, you know what the star looks like without the planet, and then you know what the star looks like with the planet in front of the star, and you can use that to get a sense of what are the characteristics of the atmosphere. But the other kind of observation that they can make is they can do what's called an eclipse observation. And so this is the other part of that orbit, when the planet is passing behind the star. And what's amazing about that is that you get sort of two opportunities. You get to watch as the planet is passing behind the star, and it's getting less and less and less. And so you're seeing the signal of its atmosphere decreasing until it's gone. And then it reappears again on the other side of the star, and you get to add that together. And so the problem is that astronomers never get to see like the star and then the planet, and then they separate the star away and they just look at the planet. It's always this combination. They have to tease out the chemicals from the atmosphere. They have to see which of the star's light is being absorbed by the atmosphere of the planet to be able to get a sense of what those chemicals are in the atmosphere of the planet. So long story short, they did those observations with TRAPPIST-1c, and again, nothing. So TRAPPIST-1d, this is the first planet that is in the habitable zone around the TRAPPIST star, this red dwarf star. And then you've got E, and then you've got F, at least 3 planets in the habitable zone. And we've been waiting a long time for this. And my assumption, and you know, the interviewer that I was talking to today didn't work on that, so he has no inside information. But my sense of this is that it's a very complicated, very important observation to make. And we've seen plenty of examples in the past where people got the science wrong, or they got it inconclusive. Like think about the Viking landing, think about the discovery of methane on Mars, think about the Allen Hills meteorite where they thought they'd found life on Mars, think about phosphine in the atmosphere of Venus. Think about all of these different observations that have been made where somebody said, we did it, we found life, right? And then other scientists come through and they more carefully look at the data and they go, well, maybe you should walk that back, and it's kind of inconclusive. So people have learned their lesson. And so when they present their findings with the TRAPPIST-1 system, they're going to be very, very careful. They're going to make sure that they don't make any outrageous claims if they find an atmosphere, if they find water vapor in the atmosphere, if they find methane in that atmosphere. Like they're going to say what they found, but they're not going to go into a lot of conclusion about what it is they found, although people are going to freak out anyway. So we're kind of getting to the point though where all of the data that was gathered from James Webb on the TRAPPIST planets is going to start being publicly available to other researchers. And so if the people who took this data don't do their result, then other scientists are going to be able to work with this data and analyze it and come up with an answer. So it's going to be soon. Like we're definitely getting to the point now where it's time to hear about the other planets in the TRAPPIST system. I don't know how it's going to turn out, but I am definitely on the edge of my seat. Marco Mitrick, do you think we will ever become a Type 2 civilization, and why not? Well, I didn't say that I didn't think we would. So what is a Type 2 civilization, right? You know, the Kardashev scale, you've got Type 1 civilization. They use all of the energy that falls from the sun onto their planet. Type 2, they're using all of the energy that's emitted by the star. Type 3, they're using all of the energy that's emitted by all of the stars in their entire galaxy. Will we become a Type 2 civilization? The answer is we don't know. But what we do know is that throughout human history, humanity has used more and more energy. There is this smooth exponential curve that goes back more than 10,000 years, from when we were a hunter-gatherer society to when we were having agriculture to the steam age to modern, to oil, to renewables, to nuclear, like all these things, our energy use just continues to go up. And so you can chart the energy use of humanity into the future, and then you can make some predictions. If you just assume that same growth, then you can actually predict the date when we will become a type 1 civilization, when we will be using all of the energy that's falling on planet Earth. And you can predict the date when we will become a type 2 civilization, when we're going to use all of the power that is coming out of the sun. And it's not long, like type 1 civilization, a few hundred years, type 2 civilization, a few thousand years. And this is the point where you say, come on, that's ridiculous. How do we know that human beings are going to use more energy in the future? Like, what if we just finally get our act together and we live in harmony with nature and we don't continue to use energy? Yes, of course, right? We could be on an S-curve, and the S-curve reaches the top of the S-curve and then it just declines. And maybe we go back down to the agricultural age again and we never build a Dyson sphere. Fine. But maybe we just continue. That energy use is an exponential path that we will follow to its inevitable conclusion, which is that we will use all of the available energy and matter in the accessible universe, which is about 4% of the observable universe. It's a lot of galaxies. Who knows? And this, of course, this is the idea of the grabby aliens, that you look out into the universe and that you should see these alien civilizations that are gobbling up vast chunks of the universe at pretty much the speed of light. And we don't see that. Now, people always say Dyson spheres are ridiculous. We're never going to build a Dyson sphere. And like, Dyson knew that a Dyson sphere was ridiculous, but the Dyson swarm is the idea that most people settle on, that you're not going to build a rigid sphere. It's not stable. You're going to build a cloud of satellites that are orbiting around the sun, and they're going to be collectively gathering all of the illumination that's coming from the sun. And again, people say that's ridiculous. Fine, but we have already begun building our Dyson swarm. We have the James Webb Space Telescope. We have all of the various satellites and telescopes. Anything that is out in space right now that humanity has already built and is blocking a little bit of the sun's light from reaching deep space. That is how you start a Dyson swarm. The question is, when do we end? Either we'll end when we run out of need or we run out of space. And my money's on space. That we will just keep going. Who knows what we will use it for? This is where I'm making, are we going to be able to finally run Crisis 3? I don't know. SF. I just bought my first telescope, a 127mm reflector. Other than planets, how do I find cool targets in the sky and know how to point the telescope to see that target? So this is something that nobody tells you when you buy a telescope. And that is that there aren't a lot of things to look at with your telescope if you're in any kind of light pollution. So you buy a telescope, and 127mm, it's like, what, a 4-inch telescope? That's a great telescope. There's lots of stuff you can see. Is it a 6-inch telescope? Anyway, that's a great telescope. That was the size of my first telescope. And right away, with a couple of good eyepieces, you're able to see the moon, you're able to see the rings of Saturn, you're able to see Jupiter, you're able to see the bands across the planet, the moons of Jupiter. You can see Mars when it's at its closest point. You can see the polar ice caps on Mars. If you know where to look, you can resolve the Uranus and maybe Neptune as little blue dots, and you can see Venus as it goes through its phases. And you can maybe see Mercury as a little tiny disk, and that's it. And this is the problem, is that there actually are thousands of objects that you could look at in the night sky, but you need to know where to look, and you need to have the right kind of sky conditions to be able to do that. And those are all the deep sky objects. So there are a bunch of objects that are sort of cross that line between being really nice and accessible to people with a small telescope, and you can still see them in some levels of light pollution. And those are the star clusters. So there's some great star clusters, like the double star cluster and all of the globular star clusters, like the one in Hercules. If you're in the southern hemisphere, you've got the Omega Centauri cluster. Star clusters alone can keep you busy. There's one that looks like a little coat hanger. There's one that has a number. I forget the number, 39? Anyway, so star clusters are wonderful. But I know what you want. And you want to see galaxies. And you want to see nebulae. And the problem is that even in the best telescope, a 20-inch Dobsonian telescope, something you need a stepladder to get up and look into, most nebulae are going to look nothing but like a hazy blob in the sky. Galaxies are going to look like a hazy blob in the sky in perfect, dark, pristine conditions. That's the best that you're going to be able to do. The Ring Nebula looks pretty cool. Yeah, so I'll give them that. So I would go after star clusters. I would go after the Ring Nebula. But then for like some of the fainter stuff, you're going to have to use your imagination. You say, like, I know I'm looking at the Andromeda, and I see this fuzzy bit in the eyepiece, and that's a big spiral galaxy with dark dust lanes, but I can't really see it. Because you need to go to astrophotography to go to the next level and actually be able to see all of those really faint objects. So, but it's a process. Oh, and the other thing that you can see are comets. So most of the comets that come by every year, they're not visible to the unaided eye, but they are visible in a small telescope. They're visible in a pair of binoculars. And then the other thing that I really like is visual binaries. So there are a lot of stars out there that when you look at them with your eyes, they look just like one star. But when you look with a telescope, they actually resolve into two separate stars. And in some cases, they resolve into 4 stars. And the stars, you know that the stars, you've got 4 stars, the 2 stars are orbiting each other, and they're both orbiting around a common center of gravity. And it's amazing. There's one of these in the Big Dipper, and there's a bunch of them. And so to be able to go and like point your telescope and resolve these visual binaries or more is really satisfying to me. And so I think this is the beginning of the hobby. It's a nice introductory telescope. It's a way for you to pull this out and show people and look at the planets and the moon and some of those star clusters and deep sky objects. And then you can decide, do you want to get a bigger telescope? Do you want to try and shift over into more of an astrophotography way? There's a lot of room in this hobby, in a lot of directions. So, but yeah, I'd say there are a bunch of stuff you can start with, and you'll know pretty quickly what your telescope is capable of showing you in your light conditions and what it isn't. But I'm glad you got one. Congratulations. Bob Cohen. The Milky Way rises at an angle in our sky, which leads me to think that the plane of the solar system is offset to the plane of the galaxy. Correct? If so, why? Yeah, this is one of those things that you can have a question and then you can do a visual observation by yourself to find out the answer. And that is like, does the solar system line up with the Milky Way? And the way you check is you go out at night and you find the plane of the ecliptic. This is the place where all of the planets are passing from your perspective. And, in my mind, I can think where my plane of ecliptic is. It's to the south. I have this sort of line where I'll see all of the planets from one horizon to the other horizon. And then you think about where the Milky Way is. And so again, I'm sort of in my home, I'm sort of thinking about the Milky Way, and the Milky Way sort of crosses the plane of the ecliptic and sort of heads overhead from my perspective to the north. And so you know that the solar system and the galaxy are sort of at right angles to each other. It's not exactly, I think it's like 59 degrees or something like that. And so why? Well, this tells you something about the formation of the solar system and how it's different from the formation of the Milky Way. The Milky Way, all of the stars are lined up together in this giant disk of the Milky Way, in this giant rotating object. And so it's one formation, mostly. Like obviously all of these different galaxies came in and were consumed to add to this structure. And we even have this warp, which shows that something came in at a funny angle and the Milky Way was trying to gobble it down. But all of the planetary systems are completely random. Each one started off as a cloud of gas and dust, and then some event, a supernova shockwave or nearby kilonova or something, caused it to begin collapsing, and then it collapsed down into whatever was the average motion of all of the particles in that gas cloud, and you got a planetary system that's turning in some random direction, random spin. And this is one of the sad things about looking for exoplanets out there, is because everything is all random. And so we only get a chance to see the planets that happen to line up perfectly with us. We've got to have the star, we've got to have the planets lining up between, and we're on the other side of this observation. And really you only get that in like 1% of planetary systems. It's going to be vastly less than that for Earth-sized worlds, that are orbiting 1 astronomical unit away from the star. Any tiny little variation above or below of the planet, and you're not going to be able to see the transit. So yeah, the Milky Way and the solar system are not lined up. And it's because planetary systems form in a different process than the galaxy did. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who has already subscribed, and welcome to the recent newcomers: Christopher Bies, Tom D, Mark Thompson, Jonathan Mears, Hugh, Amy Albertson, Brett Williamson, Phil Powell, Peter W, and Jose Rafael Gomez Rodriguez. Join the club at patreon.com/universetoday. Smack dab, can any extremophiles on Earth survive if we brought them to Mars? Absolutely. This is a question that astrobiologists had, which is, are there any life forms on Earth which are capable of surviving on Mars without any changes, without having to put through some kind of evolutionary process? Can you just send them to Mars and they will thrive? And the answer appears to be yes. Now, there is an experiment on the outside of the International Space Station. What they did was they had these little boxes, and then they put little life forms into the boxes. So they put in some fungi, they put in some nematode worms, they put in tardigrades, but they also put in cyanobacteria, and then some archaea, and just like a whole bunch of extremophiles, lichens, whatever is the most extreme plants and animals and bacteria that we know of here on Earth. And then they opened up, on the outside of the station, they opened this capsule out to space. And then they let it sit there for over a year, just exposed to space. So it was exposed to the vacuum of space. The temperature changes as the International Space Station passes from sunlight to darkness to sunlight to darkness, as well as all of the radiation, although it's not as bad on the International Space Station because you're still protected by the magnetosphere, but there is still more radiation that they're going to experience. And then at the end of that experiment, they closed the lid, they brought this experiment back down to Earth, and then they took these life forms and they exposed them to Earth conditions and they exposed them to Mars conditions. And they found that almost all of them were able to pop back and keep going when they were exposed to Earth conditions. So you take a tardigrade, a water bear, you take him to space, you leave him outside the station for a year, you bring him back down, and you get him wet again, and he just gets back to work being an adorable tardigrade. But they also exposed all of these to Mars conditions. So you've got that low pressure, carbon dioxide atmosphere, lower amounts of sunlight that are falling on it. And they found that cyanobacteria can still thrive. And so, yeah, cyanobacteria, and assumed there's going to be lots of other just kinds of bacteria, very extreme forms of bacteria. They're ready to go. You take them to Mars, they can survive. Now, I wouldn't say that they're necessarily going to thrive. Like, it's not like they're going to be able to have access to forms of water. They're not going to be able to have access to, a lot of the nutrients that they're going to find here on Earth, but they're probably not going to die. And so if the right conditions show up at some point in the future, they'll probably be able to take off. If they find their way underground, if they can reach some of these like briny, liquidy areas, maybe they can keep going. If they can go to, say, Europa or Enceladus and get under the ice and get into the water, maybe they can go from there. I think it's going to be really interesting. Like if we go to Mars and we just search and search and search and comprehensively discover that there's just no life on Mars at all, then I think it would be really interesting to see what would happen if there's a way that we could actually try out different life forms on Mars and see how they do. Because I think, not just wouldn't it be cool if Mars was greener, but we could learn so much about how life got going on the early Earth when conditions were a lot more inhospitable to life than what it is now. And so you take life to a place where they're living right at the very edge. What kinds of adaptations will they come up with to survive? And then when we extrapolate that idea to other exoplanetary systems, like we have 3 examples of planets in the habitable zone just in our solar system. We have Venus, which is on the inside of the habitable zone. We have Earth, and we have Mars, which is on the outside of the habitable zone. 3 places to compare and contrast. And so as we start to run these experiments, can extremophiles exist in the atmosphere of Venus? Can extremophiles exist on Mars? We'll get a better sense of what our search for life out there in the universe might consist of. J. Allen, if time stops at a black hole event horizon, wouldn't gravity go to infinity mathematically? Time doesn't stop at a black hole event horizon. It's just about perspective. So for the person who is falling into the black hole, you experience time normally. You are falling towards the black hole, you pass the event horizon, maybe you look out into the universe, it all just goes horribly, horribly according to plan. Now, from your perspective, falling into the black hole, you are going to experience time dilation. You're going to see the universe speed up. As you get closer and closer to the black hole, you're going to see the universe just go faster and faster. And as you're just about to die and be spaghettified, you might see hundreds of quadrillions of years into the future of the universe. From an outside perspective, they're watching you fall into the black hole and you seem to just stop. And then you just redshift away and eventually you just fade away. But they don't see the spaghettification. And so from their perspective, when you think about your perspective, right, you're watching the universe in fast forward. They're watching you move in slow motion. They would have to wait hundreds of quadrillions of years to actually see that process. So it's like black holes are weird, man. Nom. Do you think Artemis will continue to the moon or will X take the reins? Right now, in 2023, Artemis 1 has completed its mission. We're waiting on Artemis 2. It's expected to fly late 2024. And then, of course, after that comes Artemis 3, 25, maybe 26. And that's when humans are going to set foot on the moon for the first time in 50 years. And the way this mission is going to work, which is very different, like when you think back to the Apollo era, you had this giant rocket described as I think Zach Queeners has described it as a skyscraper where parts of it fall off. And so you have this giant rocket that flies to the moon and it sort of drops each stage as it goes. They set foot on the moon. They ride the ascent module, they reconnect with the return capsule, they fly back to Earth, and everything that's needed is contained within that one rocket. And when you compare that to what is going to happen with Artemis 3, you're going to have the crew board their Orion capsule, they're going to get into the Space Launch System, and they're going to be launched out to the moon. And then the Space Launch System has done its job. You got the Orion capsule in this very special orbit around the moon. And then the SpaceX Starship is going to provide the human landing system for the moon. And so the astronauts will get out of their capsule, their Orion capsule, they'll get into Starship, and the Starship will take them down to the surface of the moon. They'll get out, they'll do whatever they're going to do, and they'll get back in Starship, they're going to fly back to orbit, and they're going to get back into the Orion capsule, and they're going to come back to Earth. But to get a Starship to the moon is going to require this really complicated, very elaborate process where what's going to happen is you're going to have a tanker Starship that's going to be in orbit around Earth. And then you're going to have the human landing system is going to dock to the tanker and it's going to transfer all of the cryogenic propellant from the tanker to the human landing system, and then it's going to fly to the moon. Well, to get all of the cryogenic propellant into this tanker, it's estimated that you're going to need about 15 launches of Starship, each one transferring a little more propellant to the tanker until it's full and it can transfer all of its fuel to the one that's going to go to the moon. We've never tested long-term storage of cryogenic propellants in space. We've never tested transferring cryogenic propellants from one spacecraft to another at scale in a way that continues on a mission. Like, this is an incredibly complicated engineering challenge. And NASA has done a lot of work on it, and they actually transferred a lot of the knowledge that they had to SpaceX to be able to pull this off. And so, when you ask this question, will Artemis continue to the moon or X take the reins? Artemis going to the moon is completely dependent on SpaceX delivering on the human landing system. And if there's any delays, if the storage of the cryogenic propellant doesn't work, if the transfer doesn't work, then you're going to see delays in the entire Artemis system. And hopefully that won't happen. Hopefully Starship tests again in a couple of weeks, maybe a couple of months, works flawlessly. Then they move to the tanker testing. They launch, refuel, they demonstrate they're able to land on Earth safely, and everything just proceeds according to plan. But nothing ever proceeds according to plan. These things take time, and this is an entirely new way of getting spaceships functional in space. Now, I have said many times that I'm an enormous fan of space-based refueling, that although it adds more complexity, it allows reuse of your spacecraft in space, which is a game changer, right? This is why we drive our car and then we stop at a gas station and then we keep driving our car. We don't throw out our car and get a new car, we refuel it. And so there's enormous benefit to being able to refuel, but it is a challenge all on its own. And we could spend the next 20 years learning to do space-based refueling before we move on to the next step of Artemis. So now, I'm going to talk more about this because there's an interesting video that was shared and sort of goes into more detail, and I'll sort of talk about that at the end of this video. Do you think we have already achieved field propulsion technology with this UAP that we're seeing? We have no idea what we're seeing. And so unfortunately, like they are unidentified aerial phenomena. It's right there in the name, unidentified. And so right now, the best that we have to go on is we have some blurry pictures, we have eyewitness testimony from people who saw things, and then we have some analysis that has been able to identify some of these things as weather balloons, as heat signatures from aircraft, from planets, from other aircraft and things like that, and then a bunch of things which are unidentified. And so it's too early to make any kind of prediction about what's going on until you at least identify what this thing is. Like if there was a spacecraft that we could go and sit in and we could like look where the drive part is and then take that apart, and then materials engineers could try and study it and physicists could try and understand how it's generating so much energy and providing these kinds of G's, then we would have a much better grasp on what's going on. Or it could turn out that after careful analysis, and as we get better sensing out in space and on Earth, every single UAP goes away. That there is nothing that is unidentified aerial phenomena. It all becomes identified aerial phenomena. It's balloons, it's drones, it's stealth aircraft, it's all kinds of stuff. So it's just too early to know. And so my preference for now is to just say, I don't know. Let's wait for some evidence before we have a conversation about it. Visto tutti. What could grabby aliens possibly eat? Incompatible amino acids, proteins, etc. So the grabby aliens hypothesis, this is by Robin Hanson. He's of course the same guy that came up with the great filter concept for the Fermi paradox. He said that there are awful things that have happened to life in the past, and there are potentially awful things that could happen to life in the future from our position. And maybe the reason why we don't see any life forms out there in the universe is because something awful happens to every single one of them. And we've passed most of those filters already, and so what remains is the ones that are in our future, and who knows if we'll be able to pass them. And the grabby aliens hypothesis is that if these great filters don't exist, or if these great filters are not a complete 100% limitation on every single alien civilization out there, then what we should see is these expanding spheres of influence. Like think about a video game. When you play a game of like Stellaris or Master of Orion or something like that, and you start with your home world, and then you grab the worlds around you, and then you grab more of the worlds, and eventually you run up against the other civilizations, and now the entire galaxy is colonized. That's what we should see. And so, you're asking like, what would they eat? Well, most likely they're robots. That the fastest way, the most dependable, reliable, safest way to explore and exploit the largest volume of space is to send self-replicating robot probes, the von Neumann probes. What do they eat? They eat anything, and they use sunlight. So they don't care at all about your amino acids, unless they want the individual carbon, nitrogen, oxygen, phosphorus, hydrogen parts of your body, and they don't care at all about what you're made of and what you taste like. That they would just expand at close to the speed of light, consuming worlds for whatever dread purpose they have. And the fact that we don't see these grabby aliens out there in the universe can tell us some factors about our place in the universe, that we wouldn't be here to see a universe without grabby aliens if we weren't far away from grabby aliens. So we have the fact that we don't see grabby aliens gives us like one little data point about what might be a possible answer to the Fermi paradox. Andrew Mickler, what is the ideal planet type for a spacefaring species? That's a really interesting question, because there are a lot of factors. I would say, like, if you want to become a spacefaring civilization, then the thing that's most important is that you have a relatively small gravity well. Like here on Earth, with one Earth gravity, we're right at the limit of what is possible to send payloads of significant sizes into orbit. If Earth was more massive, if it was a little smaller, if the force of gravity was stronger, then we would be sending progressively less payloads to space, and eventually we get to a point where all we can send is just like a couple of 100 kilograms with a giant Saturn V type rocket. Like maybe you could bootstrap your way up from there. Like you send a robot, and then the robot goes out and starts to assemble more robots, and you can like build tethers that can try and bring your people off. But it's hard, expensive, it's complicated, it slows the process down. So you want lower surface gravity. And then you want to be in a solar system that is safe. So, when we think about being in a red dwarf star system, we got these terrible solar flares. So imagine if you were astronauts in orbit, you were trying to fly from world to world, and you would have flares that would instantly kill everybody on your spaceship whenever they went off, and they went off all the time. So you don't want that. You want a more stable star. You want a star that is larger, like the sun, or even like an F-type star, which is like a little smaller than the sun, but it's more stable than a red dwarf star. That would be the way to go. I'm trying to think what else you need for being a spacefaring civilization. For you to build up your spacefaring society in the first place, you need access to all of the raw material. You need to be able to like start fires. Like you think about some poor civilization that's underwater and they can't start fire. And that might be that they'll never be able to do that. You need to have enough oxygen in your atmosphere to allow combustion. And if you get below a certain amount, then you just can't start fires. And there's a really interesting interview that I did, and it's going to come out in a couple of days. And he was talking about how it's actually kind of weird that the Earth's atmosphere has so much free oxygen, because oxygen is so reactive. It really wants to find a home with anything that it can. And we suffer from a phosphorus deficit on planet Earth, that if we had more phosphorus on the surface of the Earth, then our life forms would be able to utilize the oxygen in our atmosphere more efficiently. And so it would actually draw down the amount of oxygen that's in the atmosphere. And if we had mountains of phosphorus, as much phosphorus as we needed, we might not actually have any oxygen in the atmosphere of Earth, because we're just using it so efficiently. And so the fact that we have a lot of oxygen in the atmosphere shows that we have kind of an inefficient biosphere, and yet it allows combustion, which is what you need to be a spacefaring civilization. So I'm sure there's like a ton of these kinds of ideas. You want to have a moon that's close by so you can practice, which is what we have. Multiple moons would be great. You want to have multiple terrestrial planets in your system that you can fly to. Ideally, they're habitable, so you can fly from world to world. You can practice setting up and living on multiple places at the same time. It's kind of interesting. Sort of imagine like a science fiction story just about some civilization that has just grown up on the perfect star system, where all of these factors are all lined up nicely. Is that the Kerbals? The Kerbal Space Program? Stephen Collins, will competition with China advance the US space program? I don't know. Like, this is different from the competition with the Soviet Union back in the 1960s, where there was a race to get to the moon. And both the Soviets and the Americans were spending just an enormous amount of their gross domestic product to be able to put human beings on the surface of the moon. When you look at the Artemis program, like, it's a tenth of the budget that was being spent on the Apollo era type budget spend. Like, they slashed the budgets, and they're never going to go back to that kind of expense. And so it is not a we must land humans on the moon at all costs, spare no expense kind of world. It's like, can we do it on a budget? Can we stretch out the timelines? Can we maybe hire some private companies to carry our astronauts to and from the surface of the moon? So there is no urgency coming from the United States in this. I don't think they see it as a race. The Chinese see it as a race. They are absolutely racing to get humans to the moon. They are absolutely racing to get samples back from Mars. I mean, already at this point, it's pretty much a done deal that the Chinese are going to bring a sample from Mars back to Earth before the Mars sample return mission is able to do it. Now, the Chinese are just going to land in one area. They're going to send up a helicopter or two and pick up samples and bring them back to the lander, and then have an ascent vehicle that brings the samples back to Earth. But it's expected they're going to launch in 2028. They'll probably have those samples back on Earth by 2031. Right now, who knows what's going to happen with the Mars sample return mission. And this is the way that China demonstrates, or feels that it can demonstrate, its technological superiority, or its technological parity, that China feels like it will have reached a level of respect and capability when it's able to have a space station that's orbiting Earth, when it's sending people to the moon. It's planning to send people to the moon by 2030, and I think they're going to be on track to do it. They're bringing samples back from the moon. They're going to bring samples back from Mars. They're going to be bringing a sample back from an asteroid, and they're just going to keep going full speed. So, it's like a race, but only one person feels like it's a race, and that's China. But I think the other half of the race is that you've got this commercial sector in the US and in Europe, even in Japan, and they are going to send humans to the moon because they can, because they have this giant capability that is being developed for spaceflight. And one of the things that the SpaceX Starship is just expected to be able to do is fly humans to the moon and back, right? Fly people to Mars and back. And so I think you're not going to see it necessarily going to be NASA versus China. It's going to be NASA's going to do its thing at its own pace based on the budget that it gets, in a very careful and diligent manner, based on the requirements set by Congress, with the providers that have been chosen for them. And they're going to be partnering with these companies that are more entrepreneurial, they're working faster. And then on the flip side, you've got what's happening in China. And that's kind of the race. I'm going to talk some more about Artemis and a video that you should watch. But first, I'd like to thank our patrons. Thanks to Hey Twyla, Dougie Stewart, Stephen Krasaki, David Richards, Mark Anstis, Joel Yancey, Antonio Lofilara, Dustin Cable, Vlad Chiplin, Modzo, George, David Giltan, Andrew Gross, Jeremy Mattern, Josh Schultz, and Jordan Young, who support us at the Master of the Universe level, and all of our other supporters on Patreon. So I don't know if you've seen this yet, but there's a great video that's making the rounds on YouTube, and that's by Destin Sandlin from Smarter Every Day. And Destin's a great guy. I consider him a friend. He invited me to Alabama once to join an amazing conference, and we had a great time, and with several hundred other science YouTubers and communicators. And he gave a presentation at the Astronautical Society about his concerns with the upcoming Artemis missions and sort of what are some of the technical challenges. And this isn't the first time that people have expressed this, but it was great for Destin to give this presentation in front of a lot of the decision makers who are dealing with this. And he made a lot of great points. And I think one of the things that should really stick is just how reliant Artemis is on Starship and how many launches it's going to take to be able to refuel Starship and to be able to go to the moon. And there's a lot of new complexity and risk and challenge that's being added to Artemis that is different from what happened with the original Apollo era. Now, it could all work out great, but there could be some additional roadblocks and problems down the road. So it's a fantastic interview. I highly recommend it. Destin is good people, and I think you're going to get a lot out of that presentation. All right, we'll see you next week.